For half a century, the standard model of particle physics has been our map to the universe. It is the most successful theory in human history, predicting the building blocks of matter with terrifying precision. It tells us there are three types of neutrinos: the electron, the muon, and the tau. Ghostly particles that flood the cosmos, passing through the Earth as if it were glass. But 30 years ago, in a laboratory buried beneath Los Alamos, we saw something that shouldn't exist: a crack in the map, an excess of events that the standard model could not explain. It whispered of a fourth player, a particle that interacts with nothing but gravity, a sterile neutrino. If real, it would rewrite the laws of nature. But science is a cruel mistress, and extraordinary claims require extraordinary evidence. The mystery began with the liquid scintillator neutrino detector, or LSND. In the mid-90s, researchers observed more electron neutrinos appearing than theory allowed. They called it an anomaly. Years later, the MiniBooNE experiment at Fermilab tried to disprove it, but instead, they saw the same ghostly signature. The physics community was electrified. This wasn't just a statistical error. It looked like the footprint of a heavy, invisible twin, the sterile neutrino. This irradical particle was the perfect candidate for dark matter. It was the missing piece of the cosmic puzzle. But there was a problem. Other experiments couldn't find it. The data was conflicting, the signals murky. To solve this 30-year standoff, we needed a machine with eyes sharp enough to see the invisible. We needed MicroBooNE. To catch a ghost, you build a trap of liquid argon. This is MicroBooNE. Located at the Fermi National Accelerator Laboratory near Chicago, this machine is a technological marvel, a liquid argon time projection chamber, or LAR-TPC. Unlike its predecessors, which were like viewing the subatomic world through frosted glass, MicroBooNE is like a high-definition 3D camera. It holds 170 tons of ultra-pure liquid argon, cooled to cryogenic temperatures. When a neutrino collides with an argon atom, it unleashes a shower of charged particles. These particles ionize the argon, leaving behind trails of electrons that drift toward a wire mesh. It captures not just the presence of a particle, but its exact trajectory, its energy, and its identity. It is effectively the Hubble telescope of particle physics. The power of MicroBooNE lies in its ability to discriminate. The anomaly seen at MiniBooNE was an excess of electron-like events. But in the older detectors, an electron and a photon, a particle of light, looked dangerously similar. Both created fuzzy rings of light. If the excess was just photons, the sterile neutrino theory dies. If they were truly electrons, the theory lives. MicroBooNE's liquid argon technology allows physicists to zoom in on the vertex, the exact point of collision. They can distinguish the single track of an electron from the double track of a converting photon with unmatched precision. For years, the detector ran silently, collecting petabytes of data, recording the chaotic beauty of the universe's most elusive particles. But data is dangerous. The human brain is hardwired to see patterns where none exist, especially when you want them to be there. To prevent bias, the MicroBooNE team performed a blind analysis. For years, they worked on the algorithms and the calibration without ever looking at the signal region. They locked the answer in a digital box. Hundreds of scientists across dozens of institutions agreed. We do not open the box until we are certain our tools are perfect. The tension was palpable. Careers, reputations, and the future of physics hung on what lay inside that box. Finally, in late 2021, the moment arrived. The algorithms were frozen. The team gathered. It was time to unblind the data and face the truth. Silence. The data appeared on the screen, and the room exhaled. The spike was gone. MicroBooNE examined the MiniBooNE energy range with exquisite precision and found nothing. The excess events that had tantalized physicists for 30 years were not there in the form of electron neutrinos. The results ruled out the sterile neutrino as the sole explanation for the anomaly with 99% confidence. The ghost particle, the dark sector chordal, dissolved into the data. It was a null result. In the media, this plays as a failure, but in science, a null result is a triumph. It tells us exactly where the answer isn't. The standard model survived another assault. standing taller and more stubborn than ever before. So, is the mystery solved? Partially. We know now that the sterile neutrino, at least in its simplest form, is likely not the answer to the anomalies of the past. But the anomalies themselves, the strange data from LSND and MiniBooNE, remain a puzzle, perhaps caused by something even more exotic, or a misunderstanding of how neutrinos interact with atomic nuclei. The death of one theory is the birth of new questions. Now the torch passes to DUNE, the deep underground neutrino experiment, a detector so massive it will dwarf everything that came before. The search for new physics doesn't end here. It only goes deeper. The ghost may be gone, but the hunt for the truth is eternal.